Now let's talk about why hydrogen has been historically problematic. Jim Free mentioned in one of those broadcasts, I think the last one, I think it was later on that Saturday around 4:30 p.m., he mentioned about the summer of hydrogen in 1990. Now, I was born in January of 1990, so I have no recollection of this, unfortunately. So I had to go do some research, and I actually came across this NASA technical report server called the Summer of Hydrogen, and this is actually, this was in the publication Ask Magazine. The author is Philip Weber, who was working on the Space Shuttle, and so this is a public works use document. I can share this with you guys here, but I wanted to read this little snippet from here, and then one thing at the very end where he basically talks about the issues they had and what they did to solve the liquid hydrogen issue for the Space Shuttle and why this summer of hydrogen was such a problem. So I'm going to start reading that here, and we'll show you some beautiful images of the Space Shuttle as we do it, and the engine. Summer of Hydrogen by Philip Weber. This is in 2008 that this was posted. Ground crew veterans at Kennedy Space Center still talk about what they call the Summer of Hydrogen, the long, frustrating months in 1990 when the shuttle fleet was grounded by an elusive hydrogen leak that foiled our efforts to fill the orbiter's external fuel tank. Columbia, STS-35, was on Launch Pad A for a scheduled May 30th launch when we discovered the hydrogen leak during tanking. The external fuel tank is loaded through the orbiter. Liquid hydrogen flows through a 17-inch umbilical between the orbiter and the tank. During fueling, we purge the aft fuselage with gaseous nitrogen to reduce the risk of fire. We have a leak detection system in the mobile launch platform, which samples, via Tygon tubing, the atmosphere in and around the vehicle, drawing it down to a mass spectrometer that analyzes its composition. When we progress to the stage of tanking, where liquid nitrogen flows through the vehicle and the concentration of hydrogen approached 4%, the limit above which it would be dangerously flammable, we had a leak. And just to jump out of this real quick, flaming hydrogen doesn't have any visible flames. So that's one of the biggest, when this was scrubbed, when this leak did happen, if you're wondering why it's so dangerous, it's because there could be a fire and you would have no idea. And it's extremely flammable. So you'd have to have thermal cameras to even see, which I'm sure they did. But that's the challenge we have here. We did everything we could think of, back to the Summer of Hydrogen. We did everything we could think of to find it. And the contractor who supplied the flight hardware was there every day working alongside us. We did tagging tests, which involved instrumenting the suspected leak sources, and cryo-loaded the external tank to try to isolate precisely where the leak originated. We switched out umbilicals. We replaced the seals between the umbilical and the orbiter. We inspected the seals microscopically and found no flaws. We replaced the recirculation pumps, and we found and replaced a damaged Teflon seal in a main propulsion system detent cover, which holds the pre-valve, the main valve supplying hydrogen to the Space Shuttle main engine 3, in the open position. The seal passed leak tests at ambient temperature, but leaked when cryogenic temperatures were applied, the same thing that happened with SLS. We added new leak sensors, up to 20 at a time, and tried to be methodical in our placements to narrow down the possible sources of the problem. We even switched orbiters, sending Columbia back to the vehicle assembly building and bringing out Atlantis, scheduled to fly as STS-38. 2 shuttles on their mobile launchers passing in the night was a majestic sight, but not one you want to see if you're trying to get an orbiter launched. None of this told us where the leak was, or if we were dealing with more than one leak source. So this liquid hydrogen problem was a problem historically with the Space Shuttle RS-25 engines. Great engines. They were able to perform extremely well. They're still useful today, right? They're even performing these once they're able to fire these engines. They're actually the performance of these engines are much higher than they were when they first launched, over 100% at this point. So they're great engines. The fuel is very efficient. Obviously, the benefit of the exhaust of that being water, H2O, as it burns, is pretty amazing. But one of the things that I want to add, there's a quick quote here. I don't want to do the whole thing because you should go and read this. But on page 6, just to give you an idea, this plagued them for so long, in the whole summer. And there's a quote here that says, one member of the ground crew even volunteered to sit in the aft fuselage during fueling, wearing an oxygen supply he would carry a sensor around with him until he found the leak. It's no surprise that the proposal was vetoed on safety grounds, but he was ready to do it. That's how frustrated and determined we were. So it gives you just this whole idea of what Philip Weber and all of these people at Kennedy Space Center had to deal with, and the grounds crew and the engineers. And this is arguably one of those things that made the shuttle such an event for media vitriol and misunderstanding and just like an overall feeling of, do they know what's going on? And this fuel, while being extremely efficient, is clearly very difficult to deal with. We're seeing the same issues come back again. I'll read this last part here just to close out a little bit of this information here. This is at the end of the article here. So, but we had the seal passed all it. But how had the seal passed all its tests at the contractor? Because that, by all means, it's working well, right? Why didn't they see the leak then in testing? Since they were working so closely with us, they were able to supply the answers as soon as we understood the problem. They had tested the seals with liquid nitrogen, not liquid hydrogen. They had a good reason for that choice. Their facility in Downey, once fairly isolated, had seen Los Angeles grow around it. With schools and offices nearby, testing with hydrogen had become too dangerous. Liquid nitrogen was the safe alternative because it won't catch fire. They're also using this to purge those lines, right? But liquid hydrogen at about negative 253 degrees C is much cooler than liquid hydrogen, which liquefies at negative 196 degrees C. And also, hydrogen atoms are many times smaller than nitrogen atoms. So the seal worked fine with liquid nitrogen, but liquid hydrogen created gaps it could slip through. Hydrogen atoms are so small, they can even escape through a weld, which is crazy. I didn't even know that. The lessons we took from this experience, in addition to seeing the persistence and dedication eventually pay off, are these. Don't take anything for granted. Stay in constant communication with the hardware manufacturer, and test as you fly. On October 6, 1990, Discovery took off from Launch Pad 39B, the first launch since April. Wow, so April to October. That sounds very familiar, doesn't it? That's literally the timeline that Artemis is looking at right now. We are facing the same problem. And then at that point, other successful launches would occur in November and December. The summer of hydrogen was over.